Sure. Correct. Correct. That's it. Simple as that. Should be pretty simple. Hey, if you're an experimentalist, you're probably playing with the numbers and seeing a certain pattern that A is congruent to B mod M if and only if A is equal to B plus K times M. So it has to work out. It's just a definition of divides. Proof is really simple. I'm actually going to lay out the entire proof. You don't need to see it step by step. You really have two proofs. If and only if sucks because you have two proofs to do. It's like, sounds like it's really nice, if and only if, but it really means more work for the student. Proof 1 and proof 2. So I'm starting out, the black starts out with the first direction. If A is congruent to B mod M, I'm assuming that A is congruent to B mod M, then I'm going to prove that A is of the form B plus KM. So what does it mean for A to be congruent to B mod M? By definition, it means that M divides A minus B. Well, then there exists a K, you just write down the definition of divides, and then you add B to both sides, and you have the conclusion that A is equal to B plus K times M. Likewise, the other direction, if I start with A is equal to B plus MK, then I can reorder the equation and prove that M divides A minus B, hence A is congruent to B mod M. So these are pretty simple, just work it out. Theorem 2 is a very strange statement, the way he said it, so I kind of try to say it a little differently. What he says is that every integer is congruent to exactly one integer from 0 to m minus 1. All he's trying to say is that when you divide, let's say you divide by 2, well, the only possible remainders you're going to get are 0 and 1. Because then the next possible remainder you get, 3, is really 1 again, right? So that's what he's trying to say. And it just happens to come from the division algorithm. If you take two numbers, A and B, by the division algorithm, you know that you can express it as A equals B, M plus R, where R is bigger than or equal to 0, and R is strictly smaller than M. The remainder's got to be smaller, otherwise they haven't done the division correctly, right? You could actually divide by a higher quotient. So rearranging terms tells you that M divides A minus R, and that R is going to be limited by 0 to m minus 1. You can't go higher than m minus 1 because that defeats the definition of a remainder. So that's a pretty simple proof. This number, this remainder, is called the least residue of A mod M. So what's the least residue of 3 mod 2? 1, because the remainder that you get when you take 3 and divide it by 2 is 1. That's all they're asking for, is what's the remainder when you take the number and divide it by the mod, what you're modding by. Remainders are another way to think about those packaging of boxes. You could say to yourself, I'm going to take the number 2 and go through the integers and look at the possible remainders I could get. There's only 2. I could get a remainder of 0 or a remainder of 1. Anything that has a remainder of 0 when I divide by 2 goes into one box. Anything that has a remainder of 1 when I divide by 2 goes into the second box. Different way to think about the same packaging. So you mod 3, how many boxes would you have for mod 3? 3. You would have a remainder of 0, a remainder of 1, and a remainder of 2. 3 boxes, the numbers on the outside of the boxes are 0, 1, and 2. What goes into box number 0? Things that are perfectly divisible by 3. What goes into the box with remainder 1? You only have a remainder of 1. So 4 would go in there, for example. What goes in the next box? Remainder 2. And that's it. You've got the whole integers packaged up into 3 separate boxes. The union of those boxes gives you back the integers. So it's a partition. So now I'd like you to look at exercise 2.